Welcome to the third part of the tutorial on secure and robust machine learning models. And in this part, I'm going to now talk of potential robust ML defenses. So up till now, in the first two parts, we have seen that attacking ML models has turned out to be very easy. But unfortunately, defending against adversarial attacks is a tough nut to crack. We see that ML security inherits all of the formidable challenges of security. So, for example, there has been a lot of work on the security of computer systems, and we see that, as is excerpted from this book by Ross Anderson, building systems that continue to perform robustly in the face of malice is one of the most important, interesting, and difficult tasks facing engineers in the 21st century. So we find it very true that indeed the researchers are finding it very difficult to protect against ML models. So as an example, even though there have been thousands of work and this is an exponentially growing field, we still see that there are no completely robust solutions that exist. But there are some partially robust methods that have been proposed, and we'll be talking about the various options and approaches that people have tried. So just to illustrate how difficult it has been proving, how it has been shown, how defenses are very difficult to create, I highlight here the conference CVPR 2018, which was supposed to be held in June 2018. And a few months before that, in April 2018, a paper was uploaded by researchers at MIT and Berkeley, Nicholas Carlini and his collaborators, which showed that some of the works that were going to be presented in CVPR are in fact not as robust. They in fact showed that using two white box defenses, those were evaluated. They found that they were very ineffective. In fact, using some existing techniques, they showed that they can reduce the accuracy of the defense models to 0%. And so just to emphasize, CVPR is a very famous conference. And in fact, the defenses were broken even before the conference was held. And so this is Nicholas Carlini, who has been a nemesis of many in adversarial defenses. So he was part of the team that broke the CVPR 2018 defense. And this team has been successful in many other cases as well. So for example, in ICLR 2018, there were many defenses proposed, and this ICLR conference was in May 2018. And within a couple of months, it was shown that 7 of the defenses were broken in the assumed threat model. 6 were broken completely and 1 partially. So this actually showed that the community has a lot to learn, because these are the best papers. They did not have shoddy performance evaluation. They had very decent, rigorous works. They had decent, rigorous performance evaluation, but still their defense were found wanting. So let us initially see what are the major approaches that people have taken. We will then describe which one of them has been shown to be ineffective and which one of them is showing promise as a potential component of future robust machine learning methods. So firstly, we can think about techniques that are based on modifying data. So these techniques either modify the training data, for example, by adding more adversarial examples in the training data so that the model has seen some of these adversarial examples and has sort of become vaccinated or immune to those. The other approaches that modify data would be those that modify the test data. For example, if you are given a test example, you pre-process that in some way. So this is also another instantiation of a method that is based on modifying data. Another thing that we can try is to modify the model. So for example, we may modify the parameters or the feature learn, or we may make some aspect of the model difficult to decipher. For example, defensive distillation is an approach that has been proposed, which was later shown to be not very effective, because what it was doing was it was making the gradient of the system a little bit obfuscated so that the attackers cannot use it to launch attacks. But it was shown later that there are attacks that can still be launched despite obfuscated gradients. We can also make use of auxiliary models, and in these cases you make use of additional models. So for example, you make use of another GAN model or any other generative model for adversarial detection. So these are, broadly speaking, the approaches that people have taken. We can broadly classify adversarial defenses into two types. The first one focuses on the detection of adversarial examples. The other one is more powerful, and it actually prevents potential adversarial examples. So it turns out that even detecting adversarial examples is hard. We shall see that soon. We see some example adversarial detection techniques listed, such as ensembling, normalization, distributional detection, or PCA detection. There are some other techniques that are used for prevention, and we shall see some of these in more detail later. So, like I've just mentioned, that even the weaker problem of detecting adversarial examples is hard. In fact, this is a paper again by the group of Nicholas Carlini, who showed that adversarial examples are very difficult to detect. And 10 methods that were explicitly focused on detecting adversarial examples, they were bypassed by an adaptive adversary. So we shall see that an adaptive adversary is an adversary who has knowledge about the detection method. And it has been shown that such adaptive adversaries are quite potent. So once you know what defense is used, you can actually work around that. And this was shown here in this paper, in which the authors showed that they were able to defeat not only one or two detection methods, but 10 different top-notch papers in which detection methods were proposed. Broadly speaking, when we talk of protection, there are different types of approaches. There is one approach that makes use of ensembles, and ensembles are models in which you make use of many different models, and all of them can be potentially fragile, but the idea is that you are hoping that the model's diversity will neutralize any adversary. Unfortunately, it has been shown that because of the transferability of the adversarial examples, the same adversarial example will typically work for different models. So because of that, even ensemble models are not as powerful. And so this is a drawback to such an approach, that the property of transferability. Another approach that people have explored is to make use of pre-processing, and this would be following. This will be falling in the category of modifying the data. So you would be taking the test example and applying some sort of pre-processing, so that if the adversary has added some perturbation, it can be removed. The goal here is to get rid of the adversarial artifacts. But again, the problem here is that, okay, you can use pre-processing to get rid of attacks that people have proposed in the past. But once your pre-processing model is out there in the open, people can design a system to bypass your particular kind of pre-processing. And it is this adaptive adversary that has proven to be very difficult to protect against. Another type which people have proposed is called defensive distillation, which is effectively making use of gradient masking. So when we say gradient masking, it is in fact the use of a technique that makes the use of gradients difficult, because most of the attacks, they are launched using gradient based methods for um, navigating the loss function. So you would recall from the previous part that a typical adversary makes use of a gradient based methods to do gradient ascent on the loss function and changes the input. So the problem here is that these techniques were earlier thought to be powerful, but once the adversary knows that this is artificial obfuscation of the gradient, which is done as a defense, then the adversary can work around by making use of black box models. And these are models that do not assume that you have access to the ML model. And in fact, in a black box attack, the adversary creates alternate proxy models. And once those models are created, then the adversary has full control of those models and it can launch an attack as it desires on that. So by now, this is shown to be a weak defense and it has been badly broken. In a paper by Carlini and Wagner, this was shown to be insufficient. Another approach is to make use of highly nonlinear models, because it is there is a hypothesis that these modern deep neural networks, because they make use of activation functions like ReLU and so on, so maybe they are too linear in their boundaries, and if we make use of nonlinear models, then we can actually create systems that are more robust. But it turns out that currently, as per the practice now, it is not possible to train these models at the scale at which these modern ML models work. So they are not practical for large scale problems, and people are looking at other approaches. So just a brief aside about the defense of graded masking. So this was an approach used by many papers. In fact, this article was published called Obfuscated Gradients Give a False Sense of Security, Circumventing Defenses to Adversarial Examples, again by Carlini and his co-collaborators. They saw that a defense that uses gradient masking, in other words, it does not have useful gradients for generating adversarial examples, is known to be an incomplete defense. But despite that, seven of the defenses that were proposed in 2018 relied on this effect. So effectively, what is happening is, if we see on the right hand side of the screen, you have a loss landscape. You replace it by something that looks like it if you view it from far away, but once you focus in on different parts of the figure, you find that they are not very smooth, and it is difficult to perform gradient descent or gradient ascent on this. So this is the approach taken by gradient masking, but this has been defeated by creating alternative models, or even there are now techniques that are gradient free. They don't make use of gradients for launching attacks. So this is also shown here. The approach taken through gradient masking was to replace a smooth model with a non-smooth model. In a non-smooth model, the model does not have useful gradients, and therefore the attacker cannot use it to launch an attack. But the problem is that for both of these models, the smooth ones and the non-smooth, the black box attacks still work, and they've shown to be very potent, and they effectively have reduced the effectiveness of gradient masking as a potential solution. So coming to other approaches, some approaches that have shown to be partially effective. One approach is known as adversarial training. And the idea here is to augment the training data to also include adversarial examples. So with this, you're not only training on the original input data, but you are creating adversarial examples and you're feeding it to the model to show it that these are also some morphed versions of the input image that you should still recognize as the correct label. But this is said to be not totally satisfactory because this is effective for one-step adversarial examples only, and even an adversary who is intent on defeating the system can create further adversarial examples and still can defeat the defense, but it will be harder. So in other words, an adversary can still create adversarial samples for the new network. Another approach that people have been trying is to make use of robust optimization methods, in which you are not optimizing for the average case, but you are optimizing for the worst case. So there is a lot of literature in robust statistics and robust optimization, and people are bringing that approach to adversarial training, and they are in a way giving all different kinds of examples, adversarial examples, according to attacks that lie in a certain norm ball. And with this, you can have some sort of guarantees. If the adversary is restricted to perturbations in a certain norm ball, then the system is secure against that. But obviously, this is a big caveat because realistically, an adversary can go beyond that. So that's highlighted here, that attackers are not limited to attacks in some norm ball, but still it is the best that we can do currently. So let's see what adversarial training looks like. So as an example, this is an image of a bird which is fed into a machine learning model, and it is told that this is a bird. But then using the methods that were shown earlier for creating adversarial examples, you can perturb the image, create an adversarial example, but then also show this to the ML model during its training. Since the adversarial examples are fed to the ML model during the training, we say that we are making use of adversarial training. And we repeat this, and using this, we are showing adversarial examples to the ML model during the training, in the hope that we will be able to catch the potential adversarial examples. It remains an open question if doing this would reduce the accuracy of the ML model. And there are some results which are showing that if you show adversarial examples to the system at the training time, your accuracy on the non-adversarial examples may suffer, but through this you're learning more robust features, and effectively that has advantages for robustness. We can think of adversarial training as an advanced form of data augmentation. Let me describe here the pros and cons of adversarial training. One of the benefit is that it is a very simple approach. It is intuitive, it is easy to understand, yet it gives strong formal and empirical guarantees. The cons are that it makes certain assumptions on what attacks the attacker can launch. To a certain extent, all security analysis has to make some assumptions, but these assumptions are typically quite simplistic. So for example, we may assume that the adversary can perturb the image according to within a certain L norm. For example, it can make changes according to a certain L2 constraint, or a L not constraint, or an L infinity constraint, depending on their interpretations, as we've discussed in part 2 of our tutorial. Another kind of a perturbation you can make is to rotate the image potentially in adversarial ways, as was discussed in the earlier part of our tutorial. And you can also try with different lighting. So, but these are all assumptions, and it should be stated that it's very difficult to enumerate all possible perturbations, and whatever we assume, people can go beyond that. So another thing is that if we show these adversarial examples to the ML model, the ML model can overfit itself to this sort of noise, and because of that it may not really catch the signal in the image, and so there is this danger. There are different kinds of adversarial training methods. So for example, if you're making use of adversarial training in a very strong sense, then you would be making use of an iterative method in which you are continuously giving it examples. But then if you're making use of adversarial training in a weak sense, maybe you're using a method like FGSM to create an adversarial example. But as we've seen before, that these simple attacks like FGSM, they are single step, they are fast, but they're not very robust. If you have a strong attack and a iterative attack, then you can create more potent adversarial examples, but then it comes at a computational cost. The solution or the methods may be slow. So if you're making use of examples created by a simple technique like FGSM, then your defense is scalable, but it's not infallible. But if you're making use of a strong attack, like you are learning about adversarial examples constructed using robust optimization techniques such as projected gradient descent, PGD, the work of Midri et al., then you can say something about potential guarantees. You can say that if the adversarial example is from a certain norm ball, then you have certain guarantees against that. So I've talked about robust optimization. When we talk of robust optimization, we can differentiate between the standard loss of deep neural networks and similar models. These standard losses are defined in an expected average case sense. So for example, you are making claims about what you expect to see on an average. But when we talk of robust loss, this is defined differently. So with this, we are talking of the expected worst case loss. So this is a different mindset, and perhaps this is more in tune with the mindset that is needed by a security defender. In this, you are assuming what is the worst thing that can happen, assuming a constrained adversary which has certain restrictions on what kind of perturbation it can launch. So if we can find a classifier with a small robust loss, we can be confident about the classifier's robustness to perturbations in the set P. So this is important because this allows us to give some guarantees. But then, like I alluded to earlier, it is possible that these two things may be at conflict. So it may be that a machine learning model that gives you lesser robust loss, it may be on average slightly worse off than something that is optimized for the standard loss. And this is, in other words, the price that you pay for security. So if we see the works on robust optimization, the min-max framework is quite prominent, in which you minimize the maximum or worst case robust loss. So this sort of formalization of optimization has been done in the setting of adversarial ML by people like Madri and his group. and they've formulated this, but it turns out that this is a very difficult problem to solve because the maximization problem is non-concave and the minimization problem is non-convex. So those of you who are familiar with convex optimization would know that if you have a maximization problem that is non-concave and if you have a minimization problem that is non-convex, then it is very difficult to solve this in a tractable fashion. So there are some solutions that we can try, but many of them are restricted in what we can do scalably. So now let me talk about adversarial defenses and how do we rigorously evaluate it, because as I've mentioned, many adversarial defenses have been broken, many of them even within days or months of their launch. So it's very important now that we are working towards rigorous evaluation of these adversarial defenses. And luckily, the community has advanced and they have come up with some best practices that people should follow. So one may ask, why is it important to rigorously evaluate adversarial defenses? And the answer would be that once we are making use of ML models, we must be aware of its robustness. We can see how robust our model will be against an adversary who can potentially attack the system. We can test the worst case robustness, and we can also see how much are we progressing in terms of the ML performance towards human level capabilities. So in terms of our assumptions, it's important to be explicit about what is our assumption about the adversary. And if we assume that the adversary has full knowledge of the target model that they're trying to attack, but is not aware of the detector that the system has in place for catching adversarial attacks, we say that the attacker is launching an oblivious attack. On the other hand, an adaptive attack is one in which the adversary has not only knowledge of the target model, but also of the defense mechanism. And so recent work has shown that it is very important for a defense to assume an adaptive attacker, because doing otherwise would be fatal for your defense. It will be very easily broken. You should not only assume that the attacker is only going to behave in the way that it was behaving previously. The adaptive adversary would in fact change its strategy according to the defense you have. And it makes sense to assume that the adversary has knowledge of your system, of your defense system. And if you're able to show that despite this knowledge, your system is secure, despite whatever the adversary can try, then it gives us some confidence that we might be onto something. So the adaptive attack can be of different types. You can have a zero knowledge adversary who has no knowledge that the detector is in place. You may have a limited knowledge adversary who knows something about the given detection scheme, but not everything. And you may have a perfect knowledge adversary. So the current best practices dictate that we assume an adaptive adversary when we are rigorously evaluating an adversarial defense. And an evaluation against non-adaptive attacks would be of very limited utility. After the defense has been defined, one should proactively think about what can be done by the adversary to defeat the system. And if you, as a person who is proposing the defense, if you're able to show that all possible attacks that can be launched, if they are ineffective, then you can make some claims about the potency of your defense. So in this regard, I've highlighted two important works. So the first work is on evaluating adversarial robustness. This is by the groups at MIT and Berkeley and other places who are working on this. And the second work, which is very fresh, it is from 2020 February. It is on adaptive attacks to adversarial example defenses. People who are interested in this domain should definitely check out this work. Other guidelines for performing defense evaluations are summarized on this slide. We see that one should evaluate the defense against the strongest attack. And robustness against weak attacks is basically useless. If you can show that your defense is good against FGSM, that does not really mean much, because now many more sophisticated attacks are possible. This is again shown in the second point, that you should evaluate the proposed defense against the strongest attacks. So even though FGSM is fast, but there are more sophisticated methods that may exist where FGSM fails. In any case, FGSM is just a single step method. It's not supposed to be very potent. It's just a fast attack. The third point is you should evaluate proposed defenses against adaptive adversaries. And like I've mentioned before, you should assume that the adversary knows the defense you've put in place and it tries every trick that people have proposed, and still it is not able to defeat the system. And so the community emphasizes a lot on releasing the source code. This helps in replicating, and it also helps the potential adversaries or the community people who are focused on attacks to try to stress test your system. Common evaluation pitfalls would be things that people do wrong. It would be people who only evaluate their attack they evaluate their defense on a very weak attack such as FGSM, or they only try to show that their defense works. So this would be the case in which people are cherry picking and they're not really doing a rigorous evaluation. This is in fact a poor scientific practice. Number 3 would be failing to apply a diverse set of attacks, because now if you see the 2 papers I've highlighted, people have proposed many different kinds of attacks. So you should not launch only one kind of attack. If a gradient-based method is not working, you can try a derivative-free method. If a white box attack is not working, you can maybe try some black box attack. If a single step method is not working, you can try iterative methods and so on. Since many gradient-free attacks have been proposed, you should be making use of that. This is actually a corollary of point 3 above. And again, failing to perform a transferability attack would actually be not good practice, because if you try to do a transferability attack, if your defense is based on obfuscation of gradients, or it is making if your defense is making some assumptions about knowledge of the adversary to your ML model parameters, it can actually, if you can do this, you will be able to see if the system can be attacked in a black box setting. So we've talked a lot about adversarial examples. That was the focus of this tutorial. But I must emphasize that there are many other attacks which were not in the scope of this tutorial. Some of them focus on attacking the training data. Some of them are focused on attacking the confidentiality of the system. Some of them are focused on stealing the model. Our focus mostly has been on adversarial attack, but let me just briefly talk about other attacks. So this is a recent work which was published on the 4th of February. This is an industry-based article in which the authors polled many people in the industry. So we see that they sent questionnaires and they asked different people in organizations such as cybersecurity, healthcare, government, consulting. These are all different industries. And they tried many different organizations. Some of them were very large, more than 1,000 employees, and some of them were small and medium size. When they were asked about what kind of a ML strategy they're using, people typically replied that they make use of ML frameworks or they make use of ML as a service. Very rarely do companies make use of ML systems built from scratch. So when they were asked about their practices in terms of adversarial ML, most of them replied that they do not have a security system in place for their ML systems. 22 out of 25 people mentioned that they do not have a proper security system. So this is a big concern, and this will continue to increase in importance. And so it's important for researchers, for practitioners to work on securing the ML systems and ensuring their robustness to adversarial loss, adversarial attacks, and other kinds of attacks. All the aspects of the ML pipeline should be secured. And so another question was asked, that which attack would affect your organization the most? So interestingly, adversarial example is not very prominent here. It's roughly fifth or sixth. The poisoning attack is perhaps the one that will affect the organization the most. The model stealing attack, the model inversion attack, the backdoor or the Trojan machine learning model, those are all very critical dangers for such organizations that are making use of machine learning. So moving ahead, I think we have talked about some simple toy problems. We've talked about the adversaries being constrained, that they can make changes, but those changes are bounded by a certain maximum L2 constraint or an L infinity constraint or an L0 constraint. But it turns out that the real attacks would be novel and would not necessarily be in the norm ball. And people are already working on this. And so you would have examples of the system being exploited and the system facing many inputs that it was not trained to. So for example, we see a sign here that is dropped on the floor. So probably the machine learning model would not have seen this in its training data, but what happens when a self-driving car sees that on the road? So we will then, after seeing this, we would come to the realization that the adversarial attacks are not limited and they will keep on evolving, and we need to have a system which allows the ML systems to anticipate the designers of the ML system to anticipate such attacks and to make appropriate preparations for secure and robust ML. So we did mention about model theft, and in model theft, this is a kind of intellectual property theft in which the aim of the attacker is to extract the model parameters indirectly, possibly through queries. So a paper towards this effect has been listed on the slide. Another example is data poisoning, which is something that many industry players are worried about. And in this, the attacker has access to the training data and it can manipulate or control what the model learns. So in the first part, you would remember that we talked of the Microsoft TAE system, in which they were learning on how to converse with people using crowdsourced data, but the crowdsourced data was actually poisoning the system. So there are issues here as well. So this is an important paper regarding this has been highlighted on the slide. Another issue is known as model inversion, in which you have certain confidence values which you get when you query the system. And using this information, we are interested as an adversary to learn sensitive information relating to the training data, which is not supposed to be shared with the end user. And people have actually made use of this. This is a figure from ACM CCS 2015, in which the authors launched a model inversion attack through which they could recover an image and a training set image, basically this was confidential data which could be guessed through an inverse attack by the authors. So, some final thoughts about robust machine learning and AI. This has been a long talk, so let me just summarize my ideas and what we've discussed. So, to summarize, if we should really be worried about robust machine learning, AI, and basically the lack of robustness. So I would like to highlight here a quote by Max Tegmark, who says that, okay, if AI and machine learning is so problematic, then should we really be using AI? The point here is that AI, like other technology, is something that can be exploited for good or for bad. We should be careful. We should anticipate potential negative uses and plan for that. So Max Tegmark says that when he is asked if he's for or against AI, he replies and asks the people, in fact, if they think that fire is a threat or not, and if they are for fire or against fire. So just like human beings have conquered fire and they have learned how to productively use it while controlling its harmful effects, we should also be thinking about controlling AI, regulating it, ensuring that it's not abused, while benefiting from its various benefits that it can give to many different industries. So Tegmark further goes on to say that this actually shows how silly it is. Of course, we are for fire. In fact, in favor of fire to keep your home warm and against arson, right? The differences between fire and AI is that they're both technologies. It's just that AI, and especially super intelligence, is way more powerful. So this is one thing that is important. The other thing is, it may be that there is a trade-off between accuracy and robustness. In this humorous cartoon, you see a person is going to get a free lunch, but the person is asked to pay for the free lunch. And in fact, there is a famous adage saying that there is no free lunch. Even if someone says, as it is written in the cartoon, that this is a free lunch, there is hardly something known as a free lunch in the real world. You have to pay for something that you want to get. So for example, if you want to have a robust ML model, there may be a price that you need to pay. And there are some results that are showing that if you use adversarial training, you do not make use of all of the features, you only make use of robust features. And this sometimes gives you the advantage of robustness, but at the cost of accuracy. So it may be that you have to decide between maximizing of accuracy or maximizing of robustness. And in the real world as well, we have such trade-offs, and basically we settle these questions according to how important and how critical that thing is. If it's very critical, we may spend more on its security, compromising on other aspects. So more on the cost of adversarial robustness. If we want adversarial robustness, typically that means that we would have to make use of more complex optimization methods. They are typically more difficult algorithms to solve, and the models may also be larger. It may also be the case that you require more training data for adversarial robustness. So these are some of the initial results that people have in the field of adversarial robustness. But there are some side benefits as well. So I would refer interested people to look at the work of Medri and his group and other people who are working on adversarial robustness. It is being seen that sometimes when you make use of adversarially robust methods, you get some side benefits. It may be the case, the jury is still out, people are still researching on it, that when we make use of adversarially robust methods, it may be that the model is really learning features that are semantically important, which human beings would also classify as being important. We have come now to the end of this tutorial. This was a long tutorial. It had 3 parts. So I hope you learned something of value, and that you found this interesting. Let me now summarize the part 3 of this tutorial. We mentioned that although some robust solutions have been proposed, there are no completely satisfactory solutions that exist, and the field is ripe for good research. We also saw that the field is nascent, it's a fledgling field, and it has seen many setbacks. People have proposed defenses, but those defenses have been broken. But now anyone working in this field should actually read about the best practices that people have proposed. You should make use of the assumption of an adaptive adversary. You should compare your solutions against the best, strongest existing attacks, and focus on breaking your own defense. And for a defense paper, one should make the assumption that the attacker has knowledge of your system. You should not make unrealistic assumptions about the secrecy of your system. And one should consider all viable attacks on their proposed system and report that these fail. So thank you very much for your time and patience. I hope you enjoyed this tutorial. Thank you.